All right, let's get right into it. If you've got a computer science exam coming up, you are exactly where you need to be. Consider this explainer your ultimate high-yield masterclass on normalized floating point binary. I know, it sounds like a total minefield of shifting points and flipped bits, but today, we're breaking down the exact mechanics. More importantly, we're going to expose the specific traps where everyone seems to lose marks, so you can walk into that test with absolute confidence.
So, here's our game plan for today. We're hitting the foundations, the golden rules of normalization, converting decimal to binary, conquering those tricky negative numbers, flipping it back to decimal, and finally, your exam survival guide. Let's do this.
Section 1. Foundations of Floating Point. We're going to start by grounding this abstract concept into something you already know really well. To really get floating point binary, you have to think back to math class and scientific notation. Take the number 3000, right? In scientific notation, we write that as 3 times 10 to the power of 3. We literally placed a decimal point after the first digit to get our base value, which is called the mantissa. Then, we multiplied it by 10 to a power, the exponent, which just tells us how many places we moved that point. Well, computers do the exact same thing with binary. Since computer hardware can't literally store a physical little dot in the middle of a number, it splits the job. The mantissa holds the actual digits, and the exponent tells the computer exactly where that imaginary binary point belongs.
But wait, here's the catch. If we don't have strict rules for this, there are technically an infinite number of ways to represent a single value just by sliding that point around and changing the exponent. And computers, they are incredibly literal. Without strict rules, they basically panic. They need to know exactly where that point is meant to be. That is exactly why we normalize. Normalization acts as the strict mathematical standard. It guarantees there's only one valid way to represent a given number, which gives us maximum precision and accuracy with the limited bits we have.
Section 2. The Golden Normalization Rules. Now that we know why we do it, we need to lay down the absolute non-negotiable laws.
This right here, this is your holy grail for the exam. In normalized floating point binary, the leading bits are everything. You can spot a normalized number instantly. Every single positive normalized number must start with 0, 1. Every negative normalized number must start with 1, 0. That's it. If your final positive answer doesn't start with 0, 1, or your negative doesn't start with 1, 0, you haven't finished the job.
All right, Section 3, Converting Decimal to Binary. Let's see how this actually works in practice, step by step.
Here is your foolproof 4-step cheat code. 1. Write out the standard fixed-point binary representation of your number. 2. Slide that binary point to satisfy our golden rule, meaning shift it until the number starts with 0, 1, assuming it's positive. 3. Calculate the exponent you'd need to put the point back where it started. And 4. Store your shiny new mantissa and your exponent. Boom, done.
Okay, pencils down for a second. Listen to this carefully because this is exactly where everyone loses marks. When you're normalizing a number, let's say 6.5, you have to move the binary point to the left to get it between that first 0 and 1. But remember what the exponent's job actually is. Its whole purpose is to tell the computer how to put the point back to its original true position. If you move the point left to normalize it, you have to move it right to put it back, which means moving the point left to normalize requires a positive exponent. It's inverse logic, and if you aren't paying attention, it will absolutely catch you out.
Section 4. Conquering negative numbers. If inverse logic was the first trap, we are officially entering the danger zone for the second. Look at this comparison. Positives are straightforward, but negatives, like negative 2.5, you can't just guess the bits. You absolutely must start by writing out the positive version of the number first, then convert it into a negative using 2's complement. The quickest trick for that, start from the right side of your positive binary number, copy every bit exactly as it is up to the first 1, and then flip everything after that. Zeros become 1s, 1s become 0s. Then, and only then, do you move the point to hit your 1, 0 negative rule. Do not skip that 2's complement step.
Now, what if we're dealing with tiny fractions instead of big numbers, like 0.005 or negative 0.25? With tiny fractions, you actually have to move the binary point to the right to normalize it. And relying on our inverse logic, if we moved it right to normalize, we have to push it back to the left to restore its true value later. Moving a point left requires a negative exponent, so fractional values are always going to give you negative exponents.
And here is a massive red flag when dealing with those negative exponents. When you shift left to denormalize, you leave these empty blank spaces on the left side of your number. You absolutely have to backfill them. But beware,
Because it's a negative number, which we know from that leading one, you have to backfill those spaces with ones, not zeros. If you backfill a negative number with zeros, you literally just turned it into a positive number and wrecked the entire value.
Section 5. Binary to decimal rules. Let's flip the script and reverse engineer this whole process.
Here's your directional cheat sheet for decoding on the exam. Super simple. A positive exponent, push the floating point to the right, making the value larger. A negative exponent, pull the floating point to the left, making the value smaller, which means it's a fraction.
I know I just said this, but I'm saying it again because it's that crucial. When you're shifting left because of a negative exponent, always look at the leading bit of your mantissa. That leading bit tells you what to add. If it's a 1, meaning it's negative, you add ones, period. Adding zeros will completely destroy your answer.
Almost there. Section 6, Final Exam Survival Guide. Let's lock this all in.
Take a mental screenshot of this checklist right now. 1. Always check your leading bits first. 0, 1 for positive, 1, 0 for negative. 2. Remember the inverse shift logic when creating your exponents. Move left to normalize, exponent is positive. 3. Negatives always need 2's complement first before you shift. 4. When backfilling a left shift, use 1s for negatives, 0s for positives. And 5. When decoding, positive means right shift, negative means left shift. Nail these rules and you are golden.
So I'll leave you with this. If there really is an infinite number of ways to write a floating point fraction, how confident are you that your answer on test day is the exact one the computer expects? Normalization isn't just some annoying hurdle your teacher threw at you. It is the absolute mathematical law standing between computing precision and total digital chaos. Master it, and you are speaking the computer's exact language. Thanks for hanging out with me on this explainer, and go crush those exams.